Hi everybody, I'm Justin Hawkins and I'm here to show you the physics-informed neural network that I trained to solve the Navier-Stokes equations. So first, a little bit of background. What are the Navier-Stokes equations? They're a set of partial differential equations that define fluid flow. And in my case, I decided to look at cases that were both steady and two-dimensional. So that got rid of any time derivatives as well as any dependence on the z dimension. So these are what those Navier-Stokes equations simplify to for those 2D conditions that I said before. And they involve variables such as x position, y position, x velocity, y velocity, pressure, density, and viscosity. Here's the actual pin itself. It's actually pretty simple, and most of the effort went into programming the loss functions for this. And here is my Navier-Stokes loss function. You can pause it, but it's and look it over if you like, but it's exactly these equations that I showed you before. Just code it up. So for the first case, I did the simplest case I could think of, and that is Couette flow. And what that is you have a channel of fluid with the bottom of this channel being fixed, so no velocity at the bottom, and the top of this channel is moving at a prescribed velocity. In this case, I just chose 1 meter per second. And I started here because it's a very simple case, but also it has an analytic solution that I could compare to. And that analytic solution is right here. U is a function of y is equal to big U over h, where big U is the velocity of the top and h is the height of the channel. So it should just come out to a linear profile. And here are my results. And as expected, the pin performed pretty well. It matched those boundary conditions of no velocity at the bottom of the channel, 1 meter per second velocity at the top, and it followed a pretty linear profile. You can see it deviated here a little bit, but I can cut it some slack because I was solving it as if I didn't know that this would be only a one-dimensional problem, actually. I still gave it both of the Navier-Stokes equations, where the analytical solution, you really only need the x component. So that turned out pretty well. The next case that I ran was, oh, and here's the y velocity and pressure profiles. Both of these should really be 0, and you can see they are an orders of magnitude smaller than the x velocity were. The next case I wanted to tackle was the case of cavity flow. So in this case, it's similar to the one before in that you have a moving top, but in this case, you have basically a bucket of fluid. That is, it's bounded on 3 sides by walls, and then on the top side, the top wall is moving at some prescribed velocity. If it helps, you can think of it like a conveyor belt going over the top of this bucket. And then the reason I chose this is because it doesn't actually have an analytic solution there. So this is a little bit more challenging for the pin to solve. I imagine just off of my intuition that some kind of vortex will form in here, but I don't actually know. So I threw the pin at it, and this is the x velocity profile it came up with here on the left. You can see at the top, it's moving at a fixed velocity, and at the bottom, it gets slower. And I was actually able to find a research paper that provided some data on their calculations, their CFD calculations for what this velocity profile should look like. So what you're looking at here on the right is a velocity profile of basically from this bottom wall to this top wall right in the middle of the bucket of fluid. And what this is saying is, okay, at the bottom of the bucket, the velocity is 0, and then as you move up, it starts to move, the fluid starts to move to the left in the negative x direction, and then as you continue to move up, it begins to move the other way in the positive x direction, and that would coincide with kind of that intuition we had before of a vortex is going right here, and here more towards the top, it's moving the positive x direction where you're close to the wall that's moving, and as you go towards the bottom, that flow recirculates. So that was pretty satisfying to see. I know it doesn't match exactly, but it's undeniable that the correct behavior is there, and perhaps with better hyperparameter tuning, I would be able to better match the paper. But I was very happy to see that. So the last and most challenging case that I tackled was flow around a cylinder. So now this is no longer just fluid flow in a free field of fluid, right? It's there's an object in the middle of it, and that object was a cylinder, and I tweaked some parameters. I made up a fluid to get a low Reynolds number so that the steady case would, or my assumption that the flow is steady would be true. At a higher Reynolds number, you get unsteady flow around a cylinder. And the only additional, well, the boundary conditions I enforced were at the surface of the cylinder, the no slip condition is in effect, and that's a common fluid condition, meaning at a wall or at an object, at directly on that wall, the fluid does not flow. It's like stuck, and that's just a function of viscosity. And but as soon as you move even the smallest bit away from that surface, the fluid can move freely again. So in real life, you end up with what's called a boundary layer, and there are whole classes you can take on that. But so I just enforced that condition and threw the pin at it and had a prescribed inflow of about zero point 0.1 meters per second. And this was the first thing that the pin gave me back. And you can see it's doing something. It's definitely holding that boundary condition that I gave it, that at the cylinder surface flow should be zero, but it shouldn't be zero and it shouldn't be that low this far away from the cylinder. You can see the pressure is doing something too. So I thought, okay, maybe I add more collocation points around the surface of the cylinder. And I think I tripled the amount of collocation points I had at that point. And you can see the results were more or less the same. Still like a low velocity near the cylinder, and it increases as you move away, but that's not really what we want. So instead, I decided to give it a warm start. Uh, and that is with potential flow. So there's a analytic solution to flow around a cylinder that you can get if you assume the viscosity is zero. And the viscosity is not zero in my case, but I thought, why don't I just, for 3,000 epochs, just tell it, just learn potential flow. Learn that as you approach the front of the cylinder, the x velocity is going to drop, and then as you move over the top, it's going to increase and then drop again. Just learn that. Same thing with the y velocity. You can see what it's doing here and the pressure. And it was able to learn that really well. And then after those 3,000 epochs, I said, okay, now have viscosity, now do the no slip condition, now have the Navier-Stokes loss as well. So I didn't get rid of the potential flow, even though I knew it wasn't going to be completely correct. But it did okay. It's got some weird stuff going on, but you can still see that near the front of the cylinder, the x velocity drops to zero, and on top it goes faster, but it's still not quite right. So, oh, and this is a nice little vector field that I had, so you can kind of see like, okay, far away from the cylinder, it's moving in a straight line across, and then it does some weird stuff as it gets close to the cylinder. So the last thing I tried was to have some potential weighting, and you can see here in my training function, I have all kinds of losses from shape loss, that's the no slip condition, the boundary conditions, the Navier-Stokes conditions, and then I have this potential loss. So I still did those 3,000 epochs, just learning potential flow. But then after those 3,000 epochs, I gave it this new loss function. And I said, okay, still care about the potential loss, potential flow loss for the beginning, like while you're still learning the Navier-Stokes equations. But as the epochs go on, I want that to matter less and less. So that came as a function of this, where I did 0.995 to the power of I, where I is the epoch, times the potential loss. And what that did is as the epochs went on, it decreased that potential loss until it was basically insignificant and it was just doing the Navier-Stokes equations. And those gave the best results I was able to get. You can see zero velocity near the surface of the cylinder, faster velocity. Oh, sorry, I should say at the front and back of the cylinder, faster velocity over the top and bottom. Same thing with the Y velocity. You can see it's diverting around. Um, it's still not great, but it was great to see how well it could do. So thank you for your time. I hope you enjoyed, and I look forward to seeing you soon.